Hi everybody, in this video I want to do two example problems involving definite integrals. Before I do that, I want to go over some useful rules for integrals that will help us in these problems. The first two rules can be derived from corresponding rules involving derivatives. In this first rule, if I have the integral of a constant times a function, I can pull the constant out of the integral. In the second rule, imagine that capital F is the antiderivative of little f and capital G is the antiderivative of little g. This rule basically says that the integral of a sum is equal to the sum of the integrals. And finally, I have a shortcut rule for finding the antiderivative of x to the power of n, which turns out to be x to the power of n plus 1 over n plus 1 plus an arbitrary constant. This is valid for real n other than n equals minus 1. And if n equals 0, you can work it out and get this. With these rules in hand, let's get started on our first example. Imagine that z is some function of x. Specifically, let's imagine that z is equal to 2x. Now, before we go any further, let me say something about this notation. This does not mean z times x. This means z of x. It means that z is a function of x. This is a general statement that z is a function of x, and then this is telling you exactly how z is a function of x. Z is equal to 2x. All right, so z and z of x in this problem are interchangeable. All right, I've made a plot of z versus x, and this line here is the line z equals 2x. So what we're asked to calculate is the integral of z of x with respect to x from x equals 0 to x equals 2. So let's do that. So we go from x equals 0 to x equals 2, and I now need to plug in for my z of x function. That's 2x. This 2 is a constant multiplying our function, so the 2 can come out of the integral. So then I'd have 2 times the integral of x dx from 0 to 2. So I need the antiderivative of x. And this is x to the first power. So using our formula, if I had x to the first power, it would become x to the 1 plus 1 power. So x to the second power. And then I divide by 1 plus 1, divide by 2. All right, so this would be the result of my antiderivative calculation. Here I've got my limits, and then this is the 2 that came out of the integral according to this first rule. All right, 2 divided by 2 is 1. And so now I've got x squared evaluated at these limits, which means I plug in the top limit for x. And then I plug in the bottom limit for x and subtract them. And that comes out to 4. So the integral of our function z of x, which was 2x, from x equals 0 to x equals 2 with respect to x gives us 4. Now, we can check that because we've got a relatively simple function, and we remember that an integral is also the area under the corresponding curve. So if I've got a plot of z versus x, and I've plotted z of x versus x, the area under the z of x curve corresponding to our limits will equal the value of the integral that we've calculated analytically. So what we need to do is calculate the area of this triangle right here. Well, the area of a triangle is 1/2 times base times height. The base is 2. The height is 4. 1/2 times 2 times 4 is equal to 4. And it agrees, so it all checks out. All right, let's do another example. In our second problem, we're going to integrate the function 4y minus 3y squared, that quantity, integrate with respect to y from y equals 1 to y equals 3. So we have two terms, so this will come into play. We have constants multiplying functions, so this comes into play. And also we'll be using this shortcut rule. Instead of x's, we have y's. So what's important is that this variable is the same as this one. So I've got x to the nth power dx, but it could be y to the nth power dy or z to the nth power dz. All right, so I have y and a dy, so I'd have y to the first power dy, and for the second one, I've got y squared dy, so y to the second power dy. All right, so this formula will come into play. All right, so let's do this. And Using this, I'll take the antiderivatives one at a time. So I'm going to take the antiderivative of this term first. So antiderivative of 4y dy. Well, the 4 comes out, and then I've got the integral of y, again, with respect to y. Y to the first power dy, well, that would go y to the 1 plus 1 power, so y squared over 1 plus 1, that means over 2. So I'll have 4y squared over 2. For the second one, I've got my 3 comes out, and then I've got the integral of y squared with respect to y using the same rule. The y squared goes up 1 power to y cubed, and then I divide by that new exponent. And then all of this I have to evaluate at the limits from y equals 1 to y equals 3. Before I do that, I've got 3 divided by 3 here. That gives me 1, and 4 divided by 2 gives me 2. So I can rewrite this, and I'll just continue this over here, equals 2y squared minus y cubed, all evaluated from 1 to 3. So what this means is I need to plug the 3 in to each of the y's, then plug in the 1 in for each of the y's and subtract those quantities. So let's do that here. Let's plug in the 3's. And now we plug in the 1's. And then let's work this out. So 3 squared is 9 times 2 is 18 minus 3 cubed, that's 27. And then I've got minus this. Let's work this out. This here is just 2, and this here is just 1. 1 cubed is 1, so I've got 2 minus 1, which is 1. So all of this, I'm subtracting 1. All right, so I've got 18, and I've got negative 27 and a negative 1, so negative 28. 18 plus negative 28 is going to give me negative 10. All right. That's our result for the evaluation of this definite integral. We used the constant rule here. We used this sum rule for integrals. And then we used the x to the power of n antiderivative rule, except we had a y instead of an x. All right, I hope these examples are helpful. Thanks for watching. See you next time.